And based on this, you can look at vision. Not based on this theory, but vision really is three-stage problem. One is encoding, and one is selection, and one is decoding. Okay, and so therefore, how do I get this pointer? Print view? No, I don't want to. I don't know how to make the pointer. But anyway, so the current lectures from yesterday, today, and tomorrow is on the encoding stage. And then you realize that by tomorrow, you realize that this efficient coding theory cannot be pushed further. It's not like the whole visual system can apply the theory and then motivated the next stage, which was a different theory, and next stage. And that will be Friday and next Monday. And then next Tuesday and Wednesday will be the last stage, which is recognition, visual recognition. And then Thursday, we are going to have an overview of the history of development of vision science, and then also have question and answers prepared for the exam, okay? As well as debate on, now that we understand, or at least we listen to the lecture for this, can we have an overview of what vision science is, and how does it compare with, let's say, another discipline in physics or scientific development and so on and so forth, yeah? Okay, and during that time, we will also talk about another theory, which, as I said, is developed by Maxwell, is one of those persons who developed it. Beautiful theory, as well as some very recent current theory, and still on progress of being tested. Some are already tested, some not. Okay, and so you can say that this bit is the classical vision. Yeah, classical means not only the experiments, but also theoretical. So theoretically, usually it's always look at vision as the eye, not the brain. Okay, so what is it? The eye, as if the eye is the vision, but actually eye is just a keyboard or your mouse of a computer, and the brain is the CPU. However, in the beginning, we don't have data on the brain, so therefore, a lot of the classical theory is about the retina, the eye. And then, into the more modern part of it, that's where non-trivial cognitive factors come in, which may be unfamiliar to physicists, and that will be conceptually quite challenging. You probably realize that efficient coding theory may be mathematically a bit stretching, but conceptually it's still very classical. For physicists, you probably feel it's okay. And conceptually challenging is like you're trying to ask the question, what is memory? For example, what is consciousness? And in fact, there's no good definition of consciousness, but nevertheless, in vision, we're going to talk about awareness and act and so on. That will be what does that mean by recognition? For example, how do you experimentally measure it to make a replicable, repeatable measure or non-repeatable measure? These are scientific methods, okay? And so therefore, starting from yesterday, we were talking about efficient coding theory, treating it as a optimization problem to say what is the transform of a raw signal to satisfy what goal it is. And we applied it to understand this transform. What is the transform in, let's say, sensing, the sensor of the light, and how should this light transform this input signal to an output signal? This is one way. Or how should we distribute the cones across the retina? That's another kind of a transform. This is sampling of light, yeah? Or sampling of color. How should we put three sensors across the wavelengths of spectrum? These are all ways of transform of input raw signal into a neural signal, okay? We talked about that. And then we start to focus on things which are receptive field, because the receptive fields are extensively studied by experiments, so they are helpful for a theoretical connect with the experiment and being tested and falsified and confirmed and so on. And so therefore, in that sense, we are trying to think about receptive field as input nodes to output nodes by a matrix transform, and then this matrix needs to be optimized to minimize this objective function, okay? And so therefore, because that's what experimental measures do, what they do is they stick electrode to one neuron, which is a one neuron node here, and then they try to put different kind of input to it and see how this neuron responds. And that's the experimental data, okay? And when they measure that, they more or less get this matrix form, and let's see how we do that. And then, yesterday's lecture, we focused on a specific example of it, where the input is just 2 nodes, not 5 nodes, but left eye and right eye, and output is also 2 nodes and how it works. And today, we are going to extend this understanding with 2 nodes to n nodes and trying to, because this is what vision is, in a sense that lots of people think about image processing. Yesterday, we did not talk about image processing. We only talk about eye processing, left eye, right eye. We don't talk about whole image, okay? So today, we will go into the whole image, and some people ask, how about convolutional filter and things like that? Could they come out and things like that, okay? And then tomorrow, we are going to talk about then this efficient coding theory somehow hit the wall, cannot get further. Okay, we'll talk about in what sense it hit the wall, it cannot go further, and therefore we're motivating the next theory, okay? And so therefore, a brief reminder that in the efficient coding theory, in a general form, it's written like this. You need to optimize to find your transform K. However, a special class of K is linearistic field. In this K is a matrix. In such a case, you will be able to write this particular EK as this particular form, where all the R's have this matrix in it, yeah? So, for example, you can say this, so that O is equals to your matrix K, to your signal S, plus input noise N, then plus the encoding noise like that. And so therefore, if you want to say what is OI, OJ, you are more or less trying to average over this. You're more or less trying to kind of have an O vector kind of a thing, and then you're trying to calculate this matrix. And since O is like that, then you will find this particular matrix, let's say RO, is a function of K, yeah? And that's how you can have that this RO is a function of K, everything is a function of K, then you can optimize, okay? And then we applied yesterday to different cases, SJ. Yesterday, then we realized yesterday this can be solved analytically when the signal is Gaussian, approximated as a Gaussian. So this K is in fact, the solution of K is in fact a multiplication of 3 matrices, okay? K is a multiplication of 3 matrices, and the first matrix is a principal component decomposition, so therefore you can, and the second matrix, a diagonal matrix to make gain control for each principal component. And the third matrix is a U matrix, which is arbitrary. Okay, this arbitrariness comes from that, we have these linear algebra solution, this is a knowledge of the trace of a matrix is invariant to any orthonormal transform, yeah? So, and the determinant matrix is also invariant to any orthonormal transform. And so therefore, because your RO is actually your K, kind of a K plus, something else, okay? And so therefore, if you put the invariance transform in front of that, it will still be the same. So that means you can have a K, and then you put an orthonormal transform to it, it's invariant, okay? And so therefore, this is invariant to this transform. And so therefore, this is invariant. They're all invariant. That means you have a degenerate class of solutions. Once you find one solution, you can have any other solutions you want. Okay, that's the reason. And we are going to take advantage of that today to do something. Okay, so therefore, if we, this orthonormal matrix actually, this orthonormal matrix actually trying to make this signal independent in second-order correlation. And this is your degenerate free to choose. And we have applied it to a one-to-one matrix. We understand. And then we say, what if it's many nodes? Then we say, first of all, you do an orthonormal transform here to make all of these independent. Then you can apply the one-to-one thing to each of them in parallel. So S1, the first component, second component, third component. So this is just a rotation from the original signal to a new signal. So original vector rotated by a matrix to another vector. And each of these components is then applied again to it. Then you get the output vector. And this output vector is then subjected to this transform to get your actual output vector. Okay, so effectively you have this. Yeah.
How can we be sure that the transition that we have done from S to independent S would be like the inverse of it would also work for the independent output to the real output?
Okay, so you have this. I'm not sure whether I understand your question, but let me try to answer. You say, oh, it does answer your question. So you have, where is, this is the one. Okay. So you have this, original correlation matrix of your signal for the Si and Sj, which is the correlation of Si, Sj. Okay? And this is a matrix. And what you need is this transform to make it diagonal. Yeah? So lambda 1, lambda n. Because this has eigenvalue lambda 1, lambda 2. Lambda n, yeah? You can always find, so that's the first stage of transform. So once it becomes diagonal, that means you are having your original signal S. Now it's transformed into Ks. This is a new signal. And this new signal is not correlated with each other because these are all zero. Yeah? So is that your question?
My question is that, like, we're going into that space with everything independent.
Yeah.
And then, like, we have the independent output from it.
Yeah.
So now we're trying to go back to the real.
Yeah. When you go back, it will be dependent in some cases.
Yeah, but, like, how can we be sure that, like, the transverse gives us the real output that we were actually looking for, which was dependent, not independent?
So imagine, maybe this will come to you, okay? So the idea is, indeed, here it's still independent.
Yeah, but
okay? But once you do the transform to it, it may be dependent to each other.
I mean, like, how can we be sure that the transform that we have done to the input would work when we work as the inverse in the output? Because, like, it may not be linear.
Well, if every step is linear, the whole thing is linear. Yeah? Because this is a matrix, this is a matrix, that the whole matrix is the multiplication of the three matrices. Okay, so this is interesting to look at this. Because this is three mathematical steps in the solution. The brain does not necessarily do three steps. It can do one step. This is a one step, yeah? This to that is one step. However, in the real brain, you look at the retina, it's actually multiple steps because from the photoreceptors to bipolar cell to horizontal cell and so on. So why does it need to do multiple steps? This is because, okay, let me just show. This is because this transform, the total transform, will have to change. Okay, if you go outdoor, it would have to change. So if it's just one step, maybe it just doesn't know how to change. But if you have a lot of hardware there, anytime you change, you can change quickly. Okay, the brain may actually implement this in n steps because the hardware constraint. Okay, because it's protein, it has to be this way. It could not do it any other way, something like that. Okay, and so these 3 steps are only conceptually in the mathematics. Does that answer the question?
So
yeah.
You're considering it to be a linear.
This is only if your special class, this is linear. Okay, and then this linear is actually valid in the retina. It's quite valid. For later, it's a valid approximation. Okay, it's only an approximation. Nothing in the real world is really absolutely linear. Yeah, so it's a good approximation. Okay, and then you can do that. Good. Okay, so now, yesterday we had a 2-dimensional example when there's 2 eyes. Okay, now today let's do n-dimensional, especially into image with n pixels. Okay, so first of all, let's go, again review this 2-eye situation. We have 2 input nodes for the left eye, 1 for the right eye, and then the first transform is to into an eigenvector, because what you transform is this transform into an eigenvector of the correlation matrix. Yeah. And so the eigenvector, because this is just the eigenvector transform, yeah? Okay? And so the eigenvector of these 2 eyes with this kind of a correlation matrix is a summation of these 2, and another one is the difference of the 2. We got that, okay? And then, maybe I skipped this too fast. Yesterday we said, okay, we need this transform, very good. But what should be this G? Because what should be G1, G2, and G3? Okay? And this G1, G2, G3, remember, it depends on a signal-to-noise for each of these channels. And so we say we're going to list the signal-to-noise in the horizontal axis and this G in the vertical axis. And we realize we always order them by the highest signal as S1, second as S2. Okay? So the lambda 1 is always bigger than lambda 2, lambda 3, because this is the signal power of each of your transformed signal, yeah? Because this is the signal power, because this is the variance, okay? This is the variance of each of these components, okay? And so therefore, let's say S1 is bigger than S2 than S3. So when it's in this high signal-to-noise region, it goes up, and then low signal-to-noise region will go down. So imagine that you are in a situation when the signal noise is very high. Then they will go like this, okay? So therefore, you will have the highest gain to your principal components of the least power, and lower gain to your principal components, the most power. But if you go to dim light, it will go into that way. So you just sacrifice all these weak signal components because they are too noisy. Okay? So when there's no noise, you say, I just want to amplify the weak signals by giving it a larger gain. Okay? And therefore, when we go to the 2-dimensional case, okay, we find that when it's a high signal-to-noise region, remember, the S plus is always the higher signal and S minus the weaker signal. In a high signal noise, you want to amplify the weaker signal, so the gain to the weak signal is bigger, okay? However, when it's a low signal noise region, then the gain to the weaker signal is weaker, okay? So this is like, in a high signal to noise region, S plus is here, S minus is here, and the stronger gain to that. And in the low signal to noise region, you give stronger gain to the S plus channel. Remember, S plus channel is the summation of the 2 eyes, so it's the average. You say, well, if the light is too dim, the average of 2 eyes is good enough. Let's just forget about the difference between the 2 eyes. And difference between the 2 eyes help you to see 3D. But average is good enough, yeah, when it's too dim. But if it's bright enough, you actually want to see the difference clearly, so therefore you can decode the 3D situation. Okay?
This and S minus here the principal components? Or
The principal components, yeah, very good.
and what does the gain represent?
The gain is part of the solution. You need to, it's a diagonal matrix where, yeah. So it's like, so for example, if you measure the neuron's sensitivities, it will represent that. So for instance, if you put a neuron there and you say, what if I give the two images same to the two eyes, how does the neuron respond? And then you say every time you give input 1, it responds 2, and input 2 responds 4, and this green gain is equal to 2. But if you give the opposite image to the two eyes, you again see how it responds. And then you have a different gain. Yeah, that's how you can measure. Okay, maybe it will be more intuitive when we talk about spatial vision. Okay, we're going to talk about spatial vision because remember we give the contrast sensitivity curve. If you did the homework, you know what that contrast sensitivity curve means. But if you haven't, I will try to give you some intuition.
Does S plus and S minus here kind of conceptually represent the right eye and the left eye, or is that
The SL is the left eye, SR is the right eye.
Okay.
S plus is their summation,
Okay.
and S minus is their difference. Yeah. Okay. And that these are the eigenvectors of your original two-dimensional input, and now you have this principal component, which is another way of talking about eigenvectors. Yeah. Okay. Yeah.
What about when one eye is blind? Like, is 3D vision get affected?
Yes, when one eye is blind, then you have this correlation matrix no longer is 1, 1, but it's 1, 0.1, or 0. And therefore, your 3D vision, you don't have any 3D vision. So more or less, you have just a one-dimensional input. And when you have one dimension,
In life, when one eye is blind, they see 3D. Or
okay, so there's a little bit confusion. You do see 3D by many other cues, okay? And because you see perspective, okay, you see shadows, you also see occlusion. So this is occluding that. So these are other cues. And however, you can also have no other cue, okay? Remember that in the first lecture when I show you there's a complete random dots, and then you can, then there's no other cues, yeah? So just to remind you that what we had in the first lecture, yeah. Remember that in the very weird situation, where is it? This is session 1. Oh, where does it go? That's very strange. Obviously, I lost it. But you probably remember that I show you, yeah? So that's, there's no cue. And so the brain has lots of redundancy built in. You can have other cues to make you see 3D vision. Yeah, very good. So, yeah, therefore, okay. So we go back to this situation where we have the two eyes. Okay. Two-dimensional input, go to two-dimensional transformed eigenvector, transformed nodes which are independent. And when the high signal noise, you give more gain to the weaker channel, which is the S minus. Okay, there's a contrast. You always want contrast. Contrast is the information. Okay? But when the signal noise is too low, you just get the summation because the contrast is too noisy. Okay? And now with this, yeah?
Sorry, are the two gains normalized or constrained in some way?
The two gains, they have to satisfy the equation, remember? The gains, they have to satisfy this equation. Yeah? So the gain is depending on what is the signal noise, it gives you what gain it is. Okay?
Yeah, but their sound can be whatever, or
No. So depending on what this lambda is, you have a solution for this gain. Remember this gain was, I do not understand why, yeah. Okay, remember this gain? Yesterday we did it in one node situation. Why is it? I'm trying to get this. Okay. Yesterday we did this in one node situation. The gain was this is the equation, remember? So given the signal noise, given lambda, you have the gain exactly determined, no normalization. Yeah. So the gain comes from this equation, solving this equation. Yeah. And so now for each principal component, you give it a gain according to that equation. And I'm just today applying to this equation. Yeah. So now we know the solution. We're trying to digest it because this equation says that. So if you go, this is the equation. Yeah, you say, okay, the gain has to be like that. Remember, the gain depends only on the signal to noise. Yeah. And then we try to plot what this gain is as a function of signal to noise. And we notice that it has two factors. One factor is in this red box, which is actually a low-pass filter. Okay? It just kind of go flat until you hit the noise too much, you go down. And the other one, it goes up. And then the multiplication of them is this black curve. And that is just the equation solution. Yeah? Okay, so therefore, if you are in this region, the gain follows this here. If you go that, so we say if you're in a high signal to noise region, the gain follows like that. If it's a low signal noise region, the gain follows like that. Okay, today we just apply it. Okay, very good. So we then apply it today. Okay, so we apply it today. We say, okay, now we understand this is the case. Okay, we say, okay, now we see why the stereo vision is in the high gain situation, you give more gain. A high signal noise situation, you give more gain to the weaker channel. In the low signal to noise situation, you give more gain to the stronger channel because the weaker channel is too noisy. Okay? Now, with this understanding, we can really generalize. Today, we're going to be really powerful. Okay, we're going to generalize. So rather than think about one signal coming from the left eye, one signal from the right eye, you just say one signal I call S1, one signal for S2. S1 can be 1 pixel, S2 is just another pixel. Okay? So imagine S1 and S2 are two neighboring pixels in the image. Okay? And then they should also go to S plus and S minus because they're correlated just kind of these kind of matrix, right? Because you can imagine these two pixels have, on average, the same signal power, but they are correlated. So they have these kind of correlations, so therefore you will get S plus and S minus, exactly just as you do. Now, what is the S plus? S plus is the average of the two pixels. So when you have your low-resolution camera, have a very poor image, well, you just average over the pixels. Yeah, that's well, in your homework, I make you average the pixel, one is the field, things like that. Okay? So you will have a lower resolution image by averaging pixels. However, you can also differentiate the pixels, therefore you see the difference between the two pixels, then you get fine details of the image. Okay? So therefore, you can imagine in a high signal to noise region, you actually want to look at the details, the difference between the pixels. That's called image contrast. Okay? So when you do Photoshop, they ask you, do you want to have a contrast or do you not have contrast? When you want contrast, it's trying to do that. And you notice that if your image is very poor, don't do contrast. It will give you a complete mess. Because when your image is poor quality, you are in a low signal to noise ratio region. You do contrast, it's all noisy. Okay? Then you have to just focus on averaging. Okay, then you just get a lower resolution image because averaging gives a low resolution image. Okay, so that's the intuition. So the low noise region you want to have so therefore high signal noise region you want a small resistive field. What do I mean by small resistive field? It means like this, that, where is the, yeah. Imagine that you have two pixels, pixel number 1 and pixel number 2. Then you say, oh, I want to have contrast. Then you want a neuron to look at this as an excitatory and look at this as inhibitory. Yeah? And in such a case, it's as if this neuron's recipient is just one pixel, and this is kind of a little invisible. But in the low signal to noise region, you want this neuron to look at both pixels added up. Then this neuron recipient is bigger. That make sense? So the high signal noise, the neuron's recipient is smaller. So that will come out. Okay? And that's just the intuition. Later on, I'll give you a derivation. You can also have S1, S2 as 2 points in time, one at T1 and one at T2. Okay, and they will also have this structure. So then, therefore, in a high signal-to-noise region, you want to look at 2 times in a differentiating matter by this neuron. And this neuron will have kind of a very brief, just look at things very brief. In a low signal, the neuron will look at things for a very long time. Yeah? And imagine if you look at things for a very long time and the things keep on changing, then it's all washed out, yeah? It's difficult, yeah? So you need to be brief. The signal has to be very clear. Then, MTVs jump around, you can still see it. If it's very noisy situation or the MTV situation, you can't see it very well, okay?
In the first case, when you say that the maze is like high resolution and the low resolution, then you are meaning that the S1 and S2 are, in high resolution case, they are well separated. The values of S1 and S2, there is a difference, quite good difference.
That's right. So when a high signal noise region, you will like to look at that difference. So neurons trying to have a contrast. So remember that in the homework, I make you do the reciprocal field with center and surround. Do you remember that? This is trying to look at the contrast between center and surround. Okay? Then I also make you do the homework. I say, okay, just give a very big center and no surround. This is the low signal noise region. So this is the reason I want you to kind of have some feeling about it. And remember, if you do that only center, no surround, the whole image become low resolution. But if you do center surround, then the whole image very sharp, the contrast enhanced, like your Photoshop, enhancing contrast. Okay? So enhancing contrast only works when you have a clear, low noise image. Otherwise, it will be very messy. Okay? And so if you like, go back to the homework to get some intuition. Okay? It will be useful. And you can also make S1, S2 as two cones, red cone, green cone. So in a high signal-to-noise region, you want to have the neuron look at difference between red and green. Now, what I mean by looking at difference between red and green, if you look at difference between red and green, you actually know this is something redder, that's something greener. Okay? This is when light is very good light. But if you have low signal-to-noise region, you want to look at the summation of red and green. Then you're just looking bright and dim. Then you lose color vision, right? And so if it's very dim in the nighttime, you don't see color, not only because your cone is not active, but even when your cone is still active, you kind of lose color sense. It's because you're mixing the red color with green color, then all you see is bright and dim, and you don't see the difference, okay? Okay, this is intuition, so now let's look in spatial coding, because everybody wants to know how to do CNN and how to do image processing. So in spatial coding, what you have is, in fact, a whole image with n pixels. It could be 1 million pixels. Right? It's not 2 pixels. 1 million, the S vector is 1 million dimensional. So you list them as a 1 million dimensional vector at S1, S2, S3. Here I just use X1, X2, X3. S1 is a location on the image X1, S2 is a location on X2, and so on, yeah? So each index is also the space. So these are the image pixels. And then the first step you need to do is find its eigenvector. And turns out the eigenvectors are Fourier transforms. And I'm going to derive for you why they are Fourier transforms. Okay, the Fourier components are the eigenvectors. Okay, and then on each of these eigenvectors, so therefore, the first step when you want to do the principal component is actually a Fourier transform. Lucky us, we physicists like Fourier transform. Okay, so that's very good. And then the second component is gain control. That means on each Fourier amplitude, you amplify it or not amplify it according to the gain. Okay, according to the gain 1, gain 2, gain 3, apply to it. Remember, the gain depends on the signal to noise in each of these channels. So if there's a big signal to noise, you give a particular gain. Okay, and then you can have the freedom to do whatever your orthonormal matrix is. But turns out if you choose a particular orthonormal matrix, that's the inverse Fourier transform. That's the perfect one. Okay, and I'll tell you why that is, and then we'll come to the CNN. Okay, so that's what happens. So let me derive them for you, and that's beautiful. Okay, so the first step, we have this n-dimensional vector for the n pixels. And you have to write down the correlation matrix, which is n by n. And so it's a huge correlation matrix, okay, which has an element for ijth element, which is just the average. Here, remember, all the signals are zero mean, so therefore, forget about the mean. So this is the average between, this average is an ensemble average. You average over ensembles of an input in your environment. So therefore, your environment determines what that matrix is, okay? So imagine you live in the alien world, it's a different environment, there will be a different matrix, okay? So anyway, what could it be? Then you say, well, I'm trying to look at the correlation between the pixel I and pixel j, and of course the correlation, if you are closer together on the image, they're more correlated. If one pixel here, another pixel there, they'll be less correlated. So you can imagine this correlation actually depends on the distance between the two pixels. And that's indeed the case. You can try to do your image, and indeed that's the case. High correlation when the distance is 0. When the distance is 0, of course, it's actually the variance of that pixel. And low correlation when the distance is very high. So therefore, imagine what kind of a correlation matrix it is. So imagine you have 5 pixels. It will be 5-dimensional correlation matrix. N pixels. The correlation matrix, imagine the image is 1-dimensional, okay? So therefore, so you can imagine the correlation between this pixel and that pixel will be the same as correlation of this pixel and that pixel because the distance is the same. Does that make sense? And so therefore, the correlation here is all the same. No? So on the diagonal part is the self-correlation, that's the variance. I already take this out. And this bit is just correlation between the two neighboring pixels, and this is correlation between two next neighbor pixels, and so on. But so like this is the correlation between this pixel and that pixel, and this is the correlation between this pixel and that pixel. They should be the same. So this says that our natural images have translation invariant correlations. Okay, that's the assumption. Okay, but of course, going in the world, the correlation is translation invariant. Okay. Which is actually quite a good assumption. Just imagine these two pixels here correlate just as much as these two pixels here, as long as they have the same distance. Okay? And so therefore, if you have these kind of matrix, this matrix is called topless matrix. And with this matrix, for topless matrix, as long as they have this kind of structure, that means that the correlation between two pixels, Then you can say, oh, what could be my eigenvector transformation for that? You want to transform it such that it becomes independent, such that, okay, so let's have a look. I'll go to the detail. Imagine I make this transform actually my Fourier transform. Okay, this is your Fourier transform. Okay, so let's look in detail. The Fourier transform. And if it's act on this, it was going to make it diagonal. Okay. Now remember that if we have 2 pixels, the transform is actually this 45-degree rotation. So then it becomes a summation channel and a difference channel. Okay, the original 2 pixels, now it's n pixel. The original 2 by 2 matrix, now it's n by n matrix. Okay, and then the summation channel is the 2 adding together, and the difference channel is the 2 difference from each other. And let's have an intuition. This is summation of n pixels. Okay, this is summation of n pixels. What is it? If you sum the n pixels together, this is a DC component of your Fourier transform. Yeah, is Fourier frequency equal to 0. Okay, So, and then these are different Fourier frequencies, frequency 1, frequency 2, and all these different frequencies. I call it K1, K2. They are denoting different, various types of difference. So here, when you have only 2 pixels, there's only one kind of difference is between the two pixels. And here you have n pixels. There's all kinds of differences, which is different frequencies. Okay, so let's say it's a second frequency. This is the second eigenvector. So this is the first eigenvector, 0 frequency, second eigenvector, and so on. Okay, and frequency K2, the Fourier wave. And then it will give you the second component. Okay, first component comes from the first eigenvector projected. This vector projected to the first eigenvector give you the first component. Okay, so you say this image pixels projected onto the first Fourier wave. That's your DC. And second Fourier was, this is, yeah. So if k is equal to 0, then all of these are 1. So therefore, this is summation of all these pixels. Okay. The DC component. And these are for different frequencies for the same pixel x1. And the frequency will be all kinds of these frequencies in the full dimension, yeah? So therefore, each of this is actually the sum, yeah? Sum over x for each frequency, for each frequency. That is the Fourier transform. Okay, and of course you can also do integration. That's your Fourier transform. Okay, so I often abuse notation a little bit. Sometimes I use subscript x. Sometimes I just treat it as a function x. Yeah, so this is just a little bit abusive of my notation to make it easier. The Fourier component of the original image for frequency k. And then you can say, now what is the power of this signal? Then you do this power squared ensemble average. And that will be the eigenvector of this matrix. Okay? So therefore, the power of each of this will be the eigenvector of this matrix. This is all comfortable with everybody with the linear algebra. Is it okay? Yeah, okay. So the eigenvector of this matrix. And so therefore, you can take an image and do its power spectrum. You can see that I make the Fourier wave can be the horizontal wave and the vertical wave. And this is the zeros frequency. It's really big power. And the frequency goes higher and higher, weaker power. And that's the statistical properties of our visual scenes, because that's the property. This property comes from this correlation matrix. Once you have this correlation matrix, this is your eigenvalue spectrum. So the power spectrum of images is the eigenvalue spectrum of your correlation matrix. Yeah? Okay? And so, for arbitrary Fourier wave for a particular direction, and this is for the horizontal and vertical frequencies, okay, because frequency is two-dimensional. So when you have zeros frequencies, it's analogous to the summation channel in your stereo image. And you find that beautifully, natural images are like fractal-like. So on average, this power spectrum decays as 1 over k squared. So it's power law decay. And this is, this is on average. But this is, all of these are just data for this particular image, okay? So this is the amplitude, the actual magnitude of the frequency, go from low to high. Low frequency, notice that this is in log scale. So really high, because this is a 1 over k squared, yeah? Power spectrum. So therefore, for these frequencies of the same magnitude, they are all kind of, spread all over here. On average, it's actually this red thing. Because there's different samples. On average, it's always 1 over f squared, 1 over k squared, okay? So this is going to be useful. Why? Because they are our power signal to noise power. This is the signal power that can be used to determine our gain factor G. Okay, so therefore, now we're gonna use this the power decays, the higher frequency, less power. Now we're going to put it in here. Okay, so therefore, we are going to have low frequency ones, higher power, high frequency ones, less and less in power. So you can say in the low frequency ones, they're in the high signal to noise region. High frequency ones are in the low signal to noise region. Okay, so therefore there will be a sweet spot that's having the highest gain. And this is the location where the signal noise is around 1. Signal is equivalent to noise power. And this is signal much larger than the noise power. This is signal less than the noise power. Noise is independent. So noise is flat. Okay, noise flat. Then the noise power is constant across the spectrum. So imagine these are the high signal to noise region. You will have low gain to your DC components, but higher gain to your higher frequency bits. And this is your high frequency region. Okay, so therefore, if you plot their gain as a function of frequency, it rises up, hit here, and then drops down very quickly. That's what we had, remember, on Monday? Do you see that? Okay. So that's exactly what we have. So this is actually derived as a solution. So your brain follows this mathematical solution, just like that. Okay? And where this is depends on how far you sit. So if you sit too far, your frequency is different from the person sitting lower because, how big is this frequency on your retina, yeah? And so you may find that your peak is around here or there, it's different. But qualitatively, it's like that. Okay? And so that's how it comes out. Now we need to go to the last step. You say, now I need to have a U matrix. Why do you want to have a particular inverse Fourier transform? The reason is you don't want to have your transformed image too different from the original image. Okay? So imagine if you don't have this gain control, then you have Fourier transform, inverse Fourier transform, you go back to the original, no? Okay? So you can imagine that without a gain control, you will have very faithful transformation from one to the other, completely identity. But with gain control, it will not be exactly identity, but it will be as close as possible with gain control. Okay? So you can see that this is an image. I added some noise to it. So let me just show you how the image is. It has a...
So what's the point of the gain control step?
Yes, that's very good. What's the point of a gain control step? Okay. I cannot. But do you see that there's lots of noise? Maybe I'll show you here. This is the original image. Has lots of noise in it. After the proper gain control, you see, all the big contours are highlighted. Yeah? But the noise is washed out. Okay? So what noise is washed out? The noise in high frequency region is washed out. The noise in the low frequency region is not washed out, but you're trying to get the contrast. And that's why you get all these borders very clear. Okay, but all these salt and pepper noise disappeared. So salt and pepper noise are high frequency components. You drop down the gain, so here you don't see too much salt and pepper. But in the low frequency region, you actually see these smooth, varying contours of the object. You actually want to see their boundary, how they change. You amplify, so this is the idea of amplification. So you are amplifying this particular frequency so much stronger. Okay? You're also amplifying this frequency, this frequency, this frequency. All these frequencies are amplified. But DC you don't need. Why? DC, just the average luminance of the image, contains no information about the world. So if I look at your image, you're brighter or dimmer, doesn't matter, okay? I just want to look at the contrast between your hair, your face, you see me? So whether this image is higher, average luminance, it doesn't matter. So therefore, the average luminance is really dropped down. You don't need it. It's the contrast you need. But you don't want to keep on contrast when the signal noise is too low. Okay? That's the idea. So, and then, so we come down to the last step. Why do we need inverse Fourier transform? So the inverse Fourier transform is the last step when after you do the gain control, you want to go to O1, O2. Okay, from O plus to O minus to O1, O2. So let's go back to our stereo situation where it's two-dimensional. It's easier to visualize. Do you remember that we have the left eye input versus right eye input in the two-dimensional feature space? And then we do a 45-degree rotation, which is your eigenvector transformation, yeah? Such that your new axis is S plus and S minus, okay? And then on this new axis, you put a gain to it, G plus to the S plus, and G minus to S minus. And after you put a gain, you say, maybe it would be nice to rotate it back. You rotate it back, then you go back to that. Yeah, that's the idea. You can actually mathematically prove, that's on my textbook, so if you want to go read on my textbook, you can prove that the difference between SL and O1 and SR and O2 is the minimum. When you make this U matrix transform exactly the inverse of KO, that's your best. Okay? Intuitively, you can see if you have a inverse transform, that's the intuition. But mathematically, you can see a proof for it in my textbook. Okay? So this is the reason why inverse Fourier transform is the best. Imagine you can say, I'm going to do an identity transform. Okay, let's do identity because it's also a solution, yeah? It's one of the degenerate solutions. Imagine if this is an identity transform, then what will be your output? Your output node, each of the output node has a resistive field that's as big as your huge Fourier wave, right? That will be really tough because this particular output will be the same as that output. It will look at the whole image through a Fourier wave. The resistive field is a Fourier wave covering your whole image. And the second resistive field is another Fourier wave also covering your image, except it's a different frequency. And the third neuron and so forth, all these neurons are different Fourier waves with different gains. Now imagine if the eye has to build these resistive fields. First of all, it's too big, wasting a lot of wiring of the neurons, okay? Because each neuron is wired to every input pixel. Very wasteful. Okay. However, if you do an inverse Fourier transform, then each resistive field is very small. Okay. So they are exactly correspond. So each pixel only wire to a local region of pixels because you did this inverse. Okay. And of course, if you do not do this gain control, then each pixel only wire to one pixel original. It's an identity transform. Okay. So therefore, the K we want is actually a Fourier transform, gain control, and inverse Fourier transform. That's the idea. Okay, so let's look in detail. Your original n-dimensional vector, you get a Fourier transform. And then your G matrix is a diagonal matrix because for each of your Fourier mode, you give a gain. And they're completely independent, so therefore you give a gain. And then you do inverse Fourier transform. Okay, that's exactly what. Then you get your output. Okay? And so therefore, you can look at this output node. This output node comes from this IS column multiplied to all of this and all of that. Okay, this is the J's. Okay, this is the I's row and J's column. So this transform is this row, this is that, and this is that. I'm trying to do the matrix multiplication for you. Yeah, is it okay? It's very nice. Sometimes I see you nodding your head, and I say, okay, now I can go to the next sentence. So these are very good feedback, yeah? But if you don't nod your head, I slow down a little bit, yeah? So, but I cannot wait for everybody nod your head. So a few nodding head, I could, yeah, very good. And so therefore, you can see what is this doing? This is that, okay? And so therefore, it's a summation of Fourier waves. Summation of Fourier waves is all different frequency by this weighting function. So if you sum Fourier wave adding together, if the weighting function is 1, what do you get? Delta function, right? So if this weighting is equal for all k, then you get a delta function out. But because your weighting is not equal for all k, then you will have a, okay, that's what you get. This is your local resistive field. Looks like almost delta function. But it's a small resistive field. That's why each node is only covering, you need only very little wiring. And this wiring depends only on the difference between this node and that node. So only depends on the difference between this location and that location. What is that? That's called convolutional filter, right? So you get your convolution filter out of this, okay? So therefore, this image is a convolution of that image by this filter. That's it. Because for every neuron, it has the same resistive field except shifted in space because it's shifted in space, okay? And we got this convolution filter, which has the size determined by your peak frequency, more or less. The peak frequency has a particular wavelength that will be roughly the size of your resistive field, okay? So the size of the resistive field is related to the wavelength of your peak frequency, roughly, approximation. Okay, so the size of the resistive field is roughly the wavelength for the most sensitive frequency. Because as you imagine, this is actually a wave. The dominant wave is at this frequency. The non-dominant waves are in the other frequencies. That's why it looks like this, yeah? Okay? So now you see that this is how a spatial efficient coding can come about. It has the low frequencies that's really amplified to enhance the contrast. This is contrast, contrast, contrast. They're all contrast at different frequencies. Except for the no contrast region, you give it very little gain. Okay, but at high, you just say, okay, it's too much, I can't get it. Now, imagine that you are in an environment that is a normal environment. That's great. It looks like this. But if you go to an environment that's dimmer, it will look like that, no? So where is your peak? Your peak is at a low frequency, not a middle frequency. So if you go to dim environment, this is another curve. Okay, shall we turn off the light and have a check? Okay, so if you turn off the light or dim down, you find that you cannot, it will shift. Okay, so if you go that, then you can look at your resistive field, it will become that. Okay, you just by plugging this G to that or that G to that. So you plug that G to that, you will have this resistive field, you plug this G, it's more or less emphasizing low frequency and forget about high frequency. This is exactly emphasizing low frequency, yeah? And so this resistive field is very big. And the change in the retina from this resistive field to that resistive field takes only 1 minute, mostly within 10 seconds. So if you go from the outdoor to indoor, suddenly you can, you have to wait a few seconds, okay? You suddenly feel like you can't see. There's two things that's changing. One is your photoreceptor go from outdoor to indoor is changing its dynamic range. This I haven't talked about. The second is your retinal ganglion cell went from this to that. Okay, your ganglion cell, retinal ganglion cell, went from a small resistive field to a bigger resistive field. Okay, and if it's really too big, then you cannot see very well. But if it's not too big, you can still see well. Okay, that's what happened. Okay, so now we get an intuition, and we have like another 30 minutes. Now we can generalize. If maybe now it's a good time to take a pause. Is this okay? The intuition and the mathematics, I kind of give you kind of a gist of the mathematics. If you go to the textbook, or you can just go to the video. It actually derives these eigenvectors for you. Okay, you go to the online course, you find a particular derivation. How do you get this eigenvector, which is called decorrelation step? It must be a 10-minute video or 5-minute video. Yeah, you can find out. Okay, so yeah.
You say that if we turn off the light, we will get this shape, the blue. What if we increase a lot the light?
Then you will make it even go further. Yeah. So basically, your resistive field get even smaller because the size of the resistive field is, if you go shift further that, okay, here is, now this was, yeah. So this is called dark adaptation. So your retina adapts. So how can your retina within 1 minute go from this shape to that shape in your ganglion cell? That may be the reason why you have so many cell layers in the retina, because it has to change so fast. It needs to make optimal. Your mobile phone camera actually has a lot of these gain control built in. Okay, may not be exactly using my formula, but some kind of a gain control is built in. Okay. Sensitivity is built in. Okay. So now we can also calculate the correlation between output units. So imagine one output unit here, another output unit there. You say, what is the correlation between them? Okay, so these two correlations, okay, you can just write it out because, okay, basically it's the Fourier frequency. You just look at that. Okay, you will get this. Okay, and then you find that when the signal to noise is infinity, remember this is independent of k. Okay, because remember we have, so maybe it's a good idea to actually draw it here to keep this. So we have our GK, our GK depends on the signal to noise of the SK squared, okay? And it goes like this in the high signal to noise region and goes like that. And here, GK squared, okay? GK squared is actually 1 over SK squared, okay, in this region. While here it will drop, okay? So this is the high signal noise region, and this is the low signal noise region. And it goes like this. That means GK squared times SK squared is roughly OK squared constant. Yeah?
So if you plot G squared versus S squared, then initially you should have something linear, I mean, the straight line should be something linear.
What is linear?
The initial part. I mean, I would say that there is a linear relation between G squared and S squared.
S squared, yeah, but this solution is like that. The solution, remember, we have, yeah, so here, okay, this is actually G is always inverse of this. That's a solution.
So maybe you're plotting with respect to 1 over S1 squared.
Yeah, so I'm plotting this power, okay, and so if you do the Taylor expansion at the high signal to noise region, you find that at this region, okay, at this region, G is always inverse that. So this is called whitening.
So, but then this is high signal to noise.
That's right.
So which means that you are plotting against 1 over S1 S squared.
So this is, I always make the S squared go from high to low.
Okay.
Yeah, sorry about this, yeah. Sorry, that's why it's a high to low. I always go to the high to low. Yeah. The reason is in engineering, they always make the first principal noise high. And then, sorry about this, yeah. And so therefore, because this is the mathematical solution, you say this is a constant. So therefore, up to this frequency, up to this frequency, this is constant. Now, if this is constant, then you integrate over, that means they all have the same power. Then you integrate over frequency, you get a delta function. Yeah, and so therefore, if we go back to here, yeah, we are here. We are trying to calculate, where is it? Okay. So we are trying to calculate this over that. So therefore, if this is a constant, then you integrate in frequency, you will get a delta function. That means OX and OX prime is not correlated. Okay. So when the signal to noise is infinity, if the signal noise is infinity, they will keep going, okay? You never go down. So let's say our higher frequency is here, it keeps going. Does that make sense? Now, if the signal to noise is very high, it keeps going. Sorry, maybe I should not draw it this way. Okay, so if our input is so high that even our highest frequency is here, okay, our highest frequency, K max, is here. Then it will keep on going like this. Then our whole frequency range, OK squared, is constant. So when this is constant, then all our neurons, output neurons, will be independent of each other. So their response will be independent. That's complete decorrelation. Remember, in such a case, we will have no redundancy between one pixel's image information and another pixel's information. Remember, it's the redundancy that's costing us a lot of memory, the data rate. Yeah. And remember, I say, so for instance, in the input image, the local pixels are correlated. They're trying to tell the same thing, but you make it uncorrelated. This is complete decorrelation.
So when we don't have noise, we really don't need the pixels nearby to give us more information about the pixel we are looking for?
When you don't have noise, you can completely do this decorrelation, complete. However, when the signal to noise is finite, then you only decorrelate all the way to this frequency. That means you only decorrelate if the two pixels are further away than the wavelength of this frequency. But if the two pixels are within the wavelength, they will be correlated. So that's the intuition. Okay? So therefore, the correlation will be 0 if the distance between two pixels is more than the wavelength of that frequency. But they will be correlated if they're too close to each other. So imagine if these two pixels have their resistive field overlapping, they're going to be correlated. Roughly, it's like that. Okay? So therefore, when the signals is so high, all resistive fields are not overlapping. They're all looking at this contrast between the center and surround. They don't care about the average luminance. Okay? So that's the idea. So retinal ganglion cell activities are more correlated with each other when there's low signal to noise. Okay? And this is an example when we have a normal image with some normal amount of the pixel noise. And so here is my plot of the signal power. Okay, you actually take, this is some of the this is actually one of the homeworks you will do starting from today. So I give you original image, you then add some noise to it, random noise to it. Then the power spectrum does not go over 1 over k squared, but it kind of flattens out. Why? Because your noise, this is all overpowered by noise. At high enough frequency, it's all noise. So therefore, at low frequency, it's dominated by signal. The signal is actually the underlying red dashed line. Okay? So therefore, you want your gain curve, this G, optimal K, to cut down once the noise has to cut down. And when you do this optimal K, this is the result. But if you cut down too late, you say, oh, I keep on amplifying, then you get this. All the noise is amplified. Okay? This is why a noisy image, you do contrast enhancement, is a bad idea. However, if you cut down too early, then you have a low resolution image. It still gives you the big overall contours, but maybe too much detail is lost. This is the optimal. Okay, so where you cut down depends on where the signal to noise is. Okay, so this is the idea. It's cut down too late, it's cut down too early, and so on. Okay, that's efficient spatial coding. Now you are expert. We can do efficient temporal coding exactly the same way. Just remove x and become t. Yeah, replace x by t. You have time signal t1, t2, t2 is the n steps of time input. You do a Fourier transform, go to Fourier time Fourier components, then you do gain control, and then you do inverse Fourier transform. Except you are not allowed to do exactly inverse because the temporal filter has to be causal. Okay, so what that means is, if we go back to this reciprocal field, imagine this is not space but time. You say, oh, my response should not only depend on the time in the past, but also depend on the time in the future. That's not allowed. Okay, your neural response is not allowed to depend on the visual input in the future. So therefore, you have to have this filter causal, okay, not acausal. So if you do exactly inverse Fourier transform, it becomes an acausal Fourier reciprocal field in time. Then all you need to do is to make this causal, which is actually by a trick of putting a phase, which in engineering, people do that a lot because in engineering, everything is causal. But for the moment, you can just forget about the causalness, more or less the same. Okay? Okay, so that you need so it's the one-dimensional time rather than two-dimensional space. You need causal, temporal causality. And so just like in space, your reciprocal field can go from small reciprocal field to large reciprocal field. In time, this is a reciprocal field in time. Okay, one-dimensional in time. Again, it's trying to look at the contrast between one time and another time. Just like here, you're trying to look at the contrast between one spatial location and another spatial location. Yeah? Just like here, you're trying to look at the contrast between center and surround. You're trying to look at the, so therefore, if some things are not changing, you don't see anything. Okay, this is why in most animals, when the predators coming, they freeze, they don't move. Because if you don't move, predators cannot see you. Okay? Because predators, they have this filter, they only look at the temporal change. Okay, so if people are only looking at temporal change, you don't move, predators don't see you. Okay? But this is only in the high signal noise. In low signal noise, you will have like that. Okay, so therefore, not always the case. So therefore, it will integrate in time. This is like integrating space. Why do you want to integrate in space? You want to average out the noise, yeah? Just like here, we average out the noise when you integrate, But if you don't integrate space, you get all the noise, okay? So when you average over the local pixels, because local pixels are correlated, you boost up the signal, but average out the noise, because noise in the local pixels are independent. So you add up independent random numbers, they become 0. But you add up the correlated signal, you boost up. And this is how you boost up. Okay? So therefore, you are trying to boost up spatially, but you will lose resolution, but you will get good signal. Or you're trying to boost up temporally, then you will be a bit slow. Okay? Because imagine you need to playing ping pong, you better be turning on the light, because otherwise you cannot play ping pong. Okay, try to play ping pong in a dim situation. You'll find you're very clumsy. Why? Because your temporal signal become, integrate. You're very slow. Okay, during your lunch or dinner, whatever, you're trying to play this game. Play the game is like this. Okay, when one person hold this, another person trying to catch it. Okay, catch it. Okay. Of course, I know when to drop it, but you don't know where to drop it. You have to catch it. And so therefore, you have to be very quick. Do you like to try that with me? You drop it. Okay, I drop it. You try to catch it, okay? Okay, ready? Yeah, you can just be here, yeah. And then I'm going to drop. Oh. So your temporal filter is too slow, yeah? And so, but then try it again, and then say, Okay. And so then maybe you go, so the idea is I want you to try it until you catch it, and then you turn off the light, you certainly cannot catch it. Okay, so it's a bit dimmer. You can still see the person because your temporal filter is too slow. It's too slow. Okay, then you cannot catch it. Play that game. You can see, you say, how long do you have to wait, turn off the light, and suddenly you cannot catch it? Within 1 minute, I can guarantee you. So this, your retina really changes very quick. Okay, because this is too slow. Yeah.
What's that steep drop in as time goes on?
And so this is, again, trying to get the difference between this time duration and that time duration. It's still trying to get a difference. But here, it's trying to get a difference very close in time. So anything that'll move, you will get it, yeah? But this is a little sluggish. Why? Because the noise is too much. It needs to average over a time window to get enough signal. Then average another time window to get enough signal. Look at that difference.
No, I wasn't talking about the difference between the two plots, but in the first plot or in the second, there's like after it hits like the maximum value, there's a steep drop to the minimum value.
Can you come maybe point to it? What are you saying?
If you could go back to the first plot, like the black one, not the blue one.
You mean on this slide?
No, the K over time plot on the left.
Which one?
You just deleted.
So it's on the same slide? Do you want to come here and point to it? Or which plot?
How to interpret this drop in time?
This drop, again, comes from just like this drop. Okay, this is dropping in space, and this is dropping in time. And so therefore, this temporal duration is roughly the frequency omega on which it drops.
I think my question is, why isn't it symmetric?
Why isn't it symmetric? This is because the causality is not allowed to have non-zero values before. So this is not an inverse Fourier transform. This is an inverse Fourier transform with some phase factor so that, because otherwise if it goes like this, you are trying to depend, this is negative. Yeah, so the idea is you want to have your output at time t equals to your filter at time t minus t prime and your input at t prime. And you sum over t prime. But the t prime has to be less than t. Yeah. And so therefore, this cannot be an even function on 0. So therefore, k t minus t prime as a function of t minus t prime. It has to be 0 and then go, and not allowed to have also anything else. So this is 0. Okay, these are negative values. So you're not allowed to have. So this is as a causality in time that you don't have in space. While in space, you are allowed to have drop down to the left and to the right. They're both allowed. But in time, you're not allowed to go into the future. Answer your question? Yeah, good. Yeah, and also the width of this is more or less yeah. Okay. So, for example, if your input is something dark and then something bright turns on, then something turns off again. Let's say this is your temporal input. Then if you apply this filter on it, you can notice that this filter is on the order of 0.1, but this is 1 second. Okay, so therefore 1 second, and this is 0.1 second. So it will respond like that and respond like that. That's why if the animal freeze, then they don't have that. And then the predator do not see you. Okay, you freeze, then the predator do not see you. Okay. So this is called predictive coding. Actually, this predictive coding these days, this term is often abused. The idea is to say, okay, if I know nothing is there, I predict nothing is there, and suddenly this change is unpredicted, then it will signal to you, okay? And then if nothing is changing, you say, okay, it's like yesterday it doesn't rain, today it doesn't rain, and suddenly it rains. You only respond to change, yeah? You can just predict, if yesterday doesn't rain, today it will not rain. Huh? And so therefore, suddenly change, you go like, because this is only looking for change, okay? However, this is, sluggish, so therefore, then you can imagine that maybe this is, the change will be washed out a little bit. Yeah.
Why is the amplitude of the change to the positive number is higher to the negative number?
Really? Oh, that. Okay. And so you can, so in a sense, is like, just like here, it's more positive than negative. That means the DC is not completely zero. Okay? Because the total summation, so you have to go back, if you look at this, yeah. So if the DC is not completely to zero, then you will have a little bit of a residual overall, yeah? But if this gain is almost to zero, then you almost have the same. Yeah, very good. Okay, so now we have 5 minutes to go to something a bit more exciting. Okay, efficient color coding. So efficient color coding, now you just have three-dimensional, okay? Red, green, blue. And then now just let's forget about space, let's forget about time. And even better, lots of animals in the world, for instance, lots of monkeys only have 2 cones, not 3 cones. So you can say, oh, let's just make it just red, green, okay? Now, if it's just red, green, we can use the red, green exactly the same as our 2-dimensional case for left and right. Mathematically very similar, yeah? And then you can have the summation in one channel and difference in the other channel, just like our left and right eyes. And then you give a different gain. Now, imagine when the signal to noise is very high, which gain is higher? This higher or that higher? The color gain is higher or the luminance gain is higher? Correct, yeah. So when the signal noise is very high, you want to get the color gain higher because that emphasizes the contrast in color, yeah? And then you can just rotate it back. And this is, but if you have 3-dimensional input, red, green, blue, then you have a 3x3 correlation matrix. And then you will have to do a 3x3 dimensional decorrelation. And turns out that it is actually a luminance channel, red-green opponency channel, and a blue-yellow opponency channel. And then you give individually each of these gains, and then get that. And this is how, remember, in the first day, I say, in fact, even though your input is red, green, blue, after some processing, your brain represents it as, forget about this, as a luminance channel, and the blue-yellow channel, and red-green channel, okay? And so these are 2 different colors, different colored axes. And so when the signal's noise high, it emphasizes the color channel. When the signal noise low, it de-emphasizes the luminance channel. Okay, you can even have color adaptation. So for example, if you have a particular light that looks purple, the reason it looks purple is it activates this blue-yellow channel as well as red-green channel. It looks purple. Now imagine if you are in a night, market where there's lots of neon light and all kind of stuff, which is too much of a blue-yellow neon disco light or whatever. And so then, if you're in that, then you're going to adapt. The reason is this channel having too much of a power, it will change your gain. Yeah, because your gain depends on the power of the signal. And then it will adapt, it will go like that. Okay, so you suddenly, the purple should look reddish. So sometimes you go to a night market, you say, oh, that's a beautiful sweater, you buy it. And the next morning, the color doesn't look like it. You don't like it, you regret. Because in the morning, you have a sunlight. And in the sunlight, this 3x3 correlation matrix, remember we have this correlation matrix. Because all these depends on these 3x3 correlation matrix. And the 3x3 correlation matrix depends on your environment. So if you're in a disco environment, in a nighttime market, and in the daytime, in the sunlight, it's different. Yeah? And just like a fish in the ocean, you will have a very different color vision because the light from the waters, the sun goes in the water. First of all, dimmer signal to noise, but also blue light is filtered differently from the red light, their color environment different. And then you look at their retina color coding, different from us.
In the
Yeah.
Why do we have yellow here? Because like we have three color cones, which is red, green, and blue.
Yeah, so therefore, so the idea is what you have is these are the three. So originally you have red, green, and blue. Turns out that you get the luminance. Luminance is almost equals to the red plus green plus blue. Okay, it is the luminance. And red-green is actually roughly equals to red minus green. And blue-yellow is roughly equals to red plus green minus blue. So these become your eigenvectors. That's what happened. Yeah. And so that's what happened. Okay. And then once we understand that, now let's do the last thing before we call off for today. You say, okay, now you have separate look at the space, time, color, and everything. But in real life, everything's mixed together. So if you mix space and time, you have motion. Mix space and eye, you have disparity. So let's try one to mix space with color. It's a colorful image, okay? Just an example. We have done all these. Now let's mix space with color. So what you have is now your input is not only different location space, but also at each space x, you have 3 different cones. Okay, and then you really have to, each is a spatial function, and you need to have this matrix that you get output 3 like that. So just intuitively, but if you want to go to detail, again, you can watch the video. 3 cone images, this is just intuition. After you decorrelate in color dimensions, you get a luminous image, red-blue image, red-green image, and blue-yellow image by this orthonormal transform in 3-dimensional color space. Okay, you get that. Now, in each of these spatial images, you do your efficient spatial coding. Okay, now we know how to do efficient spatial coding. Okay, and we know exactly what is spatial residual field we need based on the spatial signal to power. So therefore, the spatial residual field for the luminous image will have different shape as the color residual field. In particular, because the luminous image has higher power, then this residual field will be the center surround small residual field. However, this will be big residual field. Why? Because the color images have weaker power. Yeah, remember the color images comes from the difference contrast, so they will have a weaker power. They have a weaker power. This have a stronger power because the summation of the signals. Okay, so therefore, these residual field will have smaller residual field. Okay, and then, as you know, that this comes from a band-pass filter in the frequency space, and this comes from the low-pass filter in the frequency space. Then you go back to the color dimension to multiplex. This is a residual field like that. This is luminance channel, so red plus green. Let's just say forget about blue. So red plus green here, and red plus green negative, red plus green positive. And this is red minus green, because this is a red minus green channel. It's bigger residual field, but it's red minus green. And if you multiplex together, if you add them together, you get, in the center, red and red add together. Positive green, negative green cancel each other, so you don't have any green left in the center. But in the surround, you have a negative green and negative green, so you have negative green. But negative red and positive red, you don't have any red left. So therefore, once you multiplex, you get that. This will be your residual field. Center excitatory. So rather than excitatory center inhibitor surround in brightness, you actually have in color. This is really quite a mixture. And you can also minus them together, you get that. And this is actually what we see in retinal ganglion cells. And so the retinal ganglion cell solution comes out of this efficient coding with this kind of multiplex. Remember, multiplex always want to do the inverse of your original thing. And therefore, you can preserve the wiring. Okay? And yeah, you can also add in blue, yellow. This will give you these kind of things. And that's it. So today, you can see that the power of efficient coding really is the same formalism that applies to the whole, whether it's stereo coding, spatial coding, temporal coding, color coding, and the whole variety, because the whole thing depends on your correlation matrix. And the correlation matrix will depend on your signal noise, depends on your species, depends on your ecological environment. So the hope is one theory explains wide variety of data, and that's the ideal. Okay, so tomorrow, then we try to push this into the cortex. And when we push this into the cortex, we will see when it applies and when it doesn't apply, and then we will kind of hit a crisis. Then we'll say, okay, crisis is also for opportunity, then we will discuss that. Okay, thank you. And for those of you who haven't signed for your attendance, please come in to add your attendance. And we will have one more homework. Tadro is,
One last thing, I will leave the solution for
I cannot click on the videos. Nothing comes out when I click on a video. Do you mean this
that's
video?
interesting.